Okay, so last time we looked at how to differentiate between orthocenter and centroid, and so today we're going to look at how to differentiate between in-center and circumcenter. We're also going to look at the relationships that we get between those two things. So just a quick reminder about what an angle bisector is. Basically, an angle bisector bisects an angle and cuts it into two congruent halves. So we would have this angle that's shown in blue, and this angle bisector would cut it into two congruent halves. So those two would be congruent. So that being said, if, for example, this angle is equal to 30, then this one would also be equal to 30. Those two halves that the angle is cut into, we would want it to be congruent. Another example may be if I have a 90-degree angle, and then I apply an angle bisector, it cuts it into two congruent halves. So obviously 90 divided by 2, this one would be 45, and this one would be 45. So that is what an angle bisector is. It cuts an angle into two congruent halves. Okay. So now we're going to get into the concurrency of an angle bisector of a triangle theorem. This basically says that the angle bisector of a triangle intersects at a point equidistant from the sides of the triangle. So here we have different angle bisectors, and I can go ahead and color coordinate them. Here's one angle bisector, here's another angle bisector, and here's another angle bisector. We know those are angle bisectors because, as you can see, they create two congruent halves. This angle would be congruent to this angle would be congruent to this angle, and this angle would be congruent to this angle. So basically, those original angles of those triangles have been cut into two congruent halves. What this theorem tells me is that those angle bisectors meet at a point that is equidistant from every single side. And so obviously we have three sides in a triangle. We have one side right here, one side right here, and one side right here. So what this theorem tells me is that that point would therefore be equidistant from all of the sides. So the distance to that side would be the same as the distance to this side, would be the same as the distance to this side. So say that I knew that the distance from this point to this point B is 3, then what that I can tell from that is that this point to this point A would also be equal to 3, and this point to this point C would also be equal to 3. So basically, what it states is that my angle bisectors connect at that point, that center point P, and that center point P is equidistant from all of my different sides, all of my sides. Okay? So that is what this theorem tells me. So that being said, we can have a problem like this. It says in triangle NOP, J is the point of concurrency of the angle bisectors. So basically, J is where all those angle bisectors intersect. Find the measure of JM. So the measure of this line right here. Well, again, what we learned in that theorem was that our point of concurrency is equidistant from all of our different sides. And so, of course, we have one side right here, and another side right here. Oops, that was my fault. And another side right here. And what it's saying is it's going to be equidistant from all those different sides. This and this and this, those would all be congruent to each other. So basically, we could say that JM would be congruent to JL, which would be congruent to JK. Right? And so we're able to find JM because what we have here is we're told that JL is equal to 5. Well, if JL is equal to 5, then JK is also equal to 5. And JM is also equal to 5. And so when we're asked to find the distance of JM, will be equal to 5. Okay, so that's basically what this theorem tells me. So please remember that it is the angle bisector is connected at a point that is equidistant on the sides. It's not telling me that the angle bisectors are congruent. Rather, the points that connect, or those lines that connect to the sides, are congruent. Okay, so don't get those confused. It is the points that connect to the sides that are congruent, or those lines that connect to the sides that are congruent. Okay. Well, obviously, what we can also tell from this triangle is we're able to find the measure of ONP. So we'll identify that angle. ONP. So ONP would be these two angles together. Well, what we know, according to the theorem that we looked at, is that J represents the points where all my angle bisectors connect. So that would mean that this is an angle bisector, this is an angle bisector, and this is an angle bisector, right? And obviously these symbols tell me that those angles have been cut into congruent halves. Okay. Well, that being said, what I want to identify is what is the measure of this angle right here. This entire angle here. Okay. And the way that we can identify is it takes two steps. First thing we want to do is identify x. Well, how do we identify x? Well, we know that that line is an angle bisector, right? This line right here is an angle bisector. So that means that those two angles would be congruent to each other. Because remember, an angle bisector cuts into two congruent halves. Which means I can put those equations congruent to each other. And that will allow me to find x. Okay. So I can solve for x by plugging it into my calculator, or I can do it algebraically. 5x equals 3x plus 20 minus 3x on both sides. 2x equals 20 divided by 2 on both sides. X is equal to 10. Okay, that's how you do it algebraically, but again, you could plug into your calculator and solve it. So now that I know that x is equal to 10, I want to plug this back in to find what exactly is my measure of these two sides. So this one was 5x minus 11. I'm just going to plug 10 back in. And that tells me that this side is equal to 39. Let us remember that those two halves of that angle is congruent, right? This angle is congruent to this angle. And so both of those would be equal to 39. So I could plug it in to the equation and see that it's also equal to 39. But because it was bisected by an angle bisector, I would know that it's also equal to 39. And so what this is asking me is to find the measure of angle ONP. So that would be the entire angle. So this entire angle. And so because of that, I want to add both of those together. 39 plus 39, 78. So that would be my missing angle. Okay, so once again, in order to solve this problem, the first thing you want to do is identify that you have an angle bisector here. You know you have an angle bisector there because of that symbol that tells me those two halves are congruent. Okay, so first thing, identify you have an angle bisector. That angle bisector tells me both of those angles would be congruent to each other, so I can use that information to solve for x. I put those two equations equal to each other, solve for x. X is 10. I want to plug it back in. That gives me that both of my congruent angles are both equal to 39, but I want the entire angle. I want all of ONP. So that means both of these angles together. So add those together, and that tells me that angle N or angle ONP is equal to 78. Okay, so that's how we would solve this one. So basically what we looked at when looking at this theorem is we looked at the point of concurrency of the angle bisectors. The point of concurrency of the angle bisectors are known as the incenter. The incenter is the center of a circle inscribed in a given triangle. The incenter is equidistant from all three sides. Remember, it's all three sides. It's equidistant for all three sides, not all three angle bisectors. We want it to be equidistant from all three sides, and it's always going to be located inside the triangle. So if we were to identify that, this is how we're going to be able to compare them. The incenter uses the concurrency of the angle bisectors of a triangle theorem. The incenter works with angle bisectors. So if you see in your question anything that has to do with angle bisectors, or it tells you it's an incenter, you know it's going to work with angle bisectors. Those two are interchangeable. We know that the incenter is equidistant from the sides. So it's equidistant from the sides, not from the angle bisectors. And in this one, we know the location is always going to be inside the triangle, no matter what type of triangle you have. Given this information, P here would be our incenter. The incenter is equidistant from all my different sides. And so obviously I have three sides. So that tells me that those three would be congruent to each other. So SP is congruent to PT, congruent to PR. And obviously I can see all my different angle bisectors, right? I have three, one right here, another angle bisector right here, and another angle bisector right there. So these lines would represent my angle bisectors. Okay, so incenters deal with angle bisectors, and incenters are going to be equidistant from the sides. Okay, questions about incenters? Okay, so now we're going to be able to differentiate that from circumcenters. Okay, so circumcenters are slightly different. We can learn about circumcenters using the concurrency of the perpendicular bisector of a triangle theorem. This theorem basically just states that the perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices. So basically, I can have various perpendicular bisectors. Remember, perpendicular bisectors just look like this. They're lines which are perpendicular. So these would be all my perpendicular bisectors. So as you see, the incenter had to deal with angle bisectors. The circumcenter has to deal with perpendicular bisectors. What this theorem is telling me is that, yes, all my perpendicular bisectors meet at that center point, the circumcenter, but what it tells me is that circumcenter is equidistant from all my vertices. Every triangle has three vertices, 1, 2, and 3. And so what this theorem is telling me is that that middle point, that P, is going to be equidistant from this vertice as it is from this vertice, as it is from this vertice. Okay, so incenter dealt with angle bisectors and its equidistance from all the sides. Circumcenter deals with perpendicular bisectors and its equidistance from all the vertices. So there you can see the differences. Okay. So solving a problem, this is an example. It says in triangle VWU, Q is the point of concurrency of the perpendicular bisectors. Because I know it has to deal with perpendicular bisectors, I know that Q is going to be my circumcenter. And then it says find the length of QV and VU. So first thing, find the length of QV. Well, what I'll notice here, okay, I know already that this is a circumcenter because why? Because it deals with perpendicular bisectors. Okay. That being said, QV, I'll notice that QV is attached to one of my vertices. Right? I have three vertices, just points at the end of the triangle. Those are my vertices. I have three vertices and QV is one of them. Well, I know that my circumcenter is equidistant from all of my vertices. And so that means that this would be congruent to this, which would be congruent to this. Am I given any measures of those? Well, yes, I'm told that QU is equal to 42. So that means that QV would also be equal to 42. And QW would also be equal to 42. Why? Because all those vertices are equidistant from that center point to my circumcenter. And so therefore, QV would be equal to 42. Okay, very similar to incenter. Remember that what this is telling you is that your circumcenter is equidistant from all your vertices. It's not equidistant from all your perpendicular bisectors. It's going to be equidistant from all your vertices. Don't get that confused, okay? So that would be 42. Now can we find VU? So it's asking me to identify VU. So that is my side VU. Well, let us remember that this symbol right here, or this line right here, is the perpendicular bisector. Let us remember that perpendicular bisectors cut our line segments into two congruent halves. And so basically VU has been cut in half by my perpendicular bisector, creating two congruent halves. And I'm given equations for those two halves, and I can write them here. Right, my perpendicular bisectors cut my line segments into two congruent halves. My angle bisectors cut my angles into two congruent halves. So that being said, because I know these are two congruent halves, I can equal these together to find y. So, because they're congruent, I can equal them together to find y. Again, I can plug this into my calculator, or I can go ahead and solve algebraically. So, 10, 6y plus 12 equals 8y minus 6y. Y is now equal to 6. So now that I know y is equal to 6, I can plug it back in. But let us remember that I want to find the entire distance of v to u. So I want to find not only the distance from v to the middle, but the middle to the other side. I want that entire distance, okay? So 6 times 6 plus 2, that's 36 plus 2, which is 38. 8 plus 6, and 8 times 6 minus 10, 48 minus 10, 38. Remember, I want to add those together to find that entire distance. That is equal to 76. Okay, so in this one, the first thing you want to identify is what side do I need to identify? Then identify that it is split into two congruent halves. That's what those symbols represent by that perpendicular bisector. And so therefore I can equal those together and find y. And then I can plug y back in to find my entire distance of v to u. Okay. And so now we can go back to this. What did we learn about circumcenter? Well, the circumcenter deals with the concurrency of the perpendicular bisector of a triangle theorem. Remember that circumcenter deals with perpendicular bisectors. It's going to be equidistant to my vertices. And, oh, I skipped that last part. Its location is going to depend on what type of triangle you have. So if it's going to be an acute triangle, it's going to be on the inside. If it's going to be an obtuse triangle, it's going to be on the outside. And it's going to be a right triangle, it's going to be on your triangle. So very similar to what we saw with orthocenter. Okay. And so circumcenter deals with perpendicular bisectors. So you'll see all these perpendicular bisectors. And what it is saying, or what the theorem told us, was that the point where all those perpendicular bisectors meet are equidistant from all of the vertices of the triangle. So there's 3 vertices. And what I guess we can also gather is that those perpendicular bisectors cut my line segments into 2 congruent halves. And so those halves would be congruent to each other. Okay. So perpendicular bisectors cut line segments into 2 congruent halves. Angle bisectors cut angles into 2 congruent halves. Incenters are equidistant from the sides. Circumcenters are equidistant from the vertices. The location of the incenter is always inside the triangle, no matter what type of triangle you have. And the location of the circumcenter depends on what type of triangle you have. So that is everything to learn. We will go over some more example problems tomorrow. But if there's no other questions, you guys may log off. Bye, guys.